Okay. Good. So let me share the presentation. Okay. Hello. Yeah.
Yes, sir.
Hello. Is this slide visible?
Yes, sir. It's visible.
Hello.
Yes, sir. The slide is visible.
Yeah. Yeah. Right. Okay. So yesterday we are discussing about this virtual memory. So any questions on that? We'll continue that today also. In the first lecture, we'll try to continue that, the concept of virtual memory and like the mapping between the related to virtual memory, that is secondary storage to like primary storage or primary memory. So those things we'll try to again discuss today in the first lecture. And then afterwards we'll move on to the second part of the course, that is operating systems. We'll start the introduction, overview, and so on. Right. So any questions? Okay. Okay. So let me very brief about the yesterday's lecture, very briefly in 5 minutes. So basically here, say the concept of virtual memory. Anyway, these details will also iterate in the next part of the course also, like in operating systems also. And here the concept of virtual memory, all of you might be aware by this time. So here the term virtual memory is basically related to, as we know that CPU can able to access up to main memory or a primary memory to access the data or instructions for execution of programs, right? And but as we know that main memory is decent enough, large enough, but it's not large enough to hold multiple programs into it. Like all the entire programs, all the programs cannot be kept in the main memory because of its limited size. Because the main memory size may be up to like maybe a range of few gigabytes, like 4 gigabytes or 8 gigabytes, right? It's of that kind of a size and all. But nowadays, some programs may have a size much larger than that. And not only that, the main memory contains the multiple programs, or the multiple users may access a single machine or a single server. In that case, the multiple users or the multiple programs also will be stored or will be placed in the main memory for its execution to perform the like multi-programming or multitasking environment. So therefore, we cannot fit or we cannot keep all the programs in a main memory, like whole programs in a main memory. So therefore, a portion of or a segment of each program or like the number of programs will be kept in a main memory so that the CPU can execute each of the program, whatever in the segment that is available in the main memory. And then when the CPU starts executing, when it refers to a memory access where that particular instruction or a data is not available, so then then again it will make use of page fault, like because it's not available. So therefore, it will be available in the at the next level of hierarchy, that is the secondary storage or the disk storage. Then using a page fault, can able to retrieve the desired page, and then place it in the memory. So in that process, again, we need to replace some of the pages. So all these things happen and all. So here the idea of main memory means actually here the CPU just see or can access the main memory. And for a system, it provides a view that even though the program is much larger than the main memory size offered by main memory, but still it provide the main memory can provide a view, like can provide a feel that it has like a sufficiently large memory, so that so any program or any number of programs you can able to run through the using a main memory by storing in the main memory and all. But actually, it's not that the entire program is stored in the main memory. A part of a program is stored in main memory, and the entire programs are actually kept in the secondary storage or the disk storage, not to be hard disk like that. right? So, but the main memory provides a view that actually it can able to hold the programs, the entire program, and can able to execute the entire the whole program at all. But the whole program is not actually there in the main memory. Only a part of that will be placed in the main memory, and the entire program is actually placed in the secondary memory, right? So that way, the main memory provides or will provide a feel that it has sufficient memory to hold the whole program or number of programs into that. It basically make use of is secondary storage. With that, it provides a concept of memory having a sufficiently large size by using a concept of not to be virtual memory. That means depending on its next level of hierarchy and all. So that way, it's not a virtual memory. That is, it means that it's not that the pro to like whatever the size of a program, that entire program is not there, or the program size will be much larger sometimes compared to the main memory size, but still you can able to execute the program using the concept of virtual memory. It means that a part of the program will be placed in the main memory and the remaining will be placed into the and the whole program, actual program is placed in the disk storage. So based on the requirement and all, you can able to swap in, swap out the segments of a program so that the program execution takes place. So it's the basically concept of it's a virtual memory. And for that, actually, here we are using a hierarchy here in the when you come to the virtual memory, it mainly focuses on like the primary storage, primary memory, and a secondary memory. It's nothing but main memory and the disk storage or a hard disk. The here the relation, or you can say the mapping between these two and all, right? Whereas earlier when you discuss about the cache memory and all, so there at that time we focus is our focus is on cache memory versus a main memory, cache memory versus main memory. And now here when you talk about virtual memory, our focus is between the main memory and the secondary storage and all. So in that context, we have discussed about like the terminology that is used in the in the context of virtual memory will be a page instead of block, right? Because the as we know that the relative sizes of main memory and secondary storage is much larger compared to cache and the main memory. So that way here the amount of the unit of data that will be transferred between the main memory and the secondary memory will be in the form of pages and all. So usually the page size will be like a typical sizes will be like 4 kilobytes, 8 kilobytes, and so on, like 16, 32, and so on, right? So that is the size of the page that is used for for transferring between the primary and secondary memory and all. And likewise here, instead of miss, suppose if the data is not present in the main memory, then we have to brought the relevant data from the secondary memory to primary memory. So where if the in that case the miss the equivalent term to the miss in context of virtual memory will be page fault and all. It means that a page is not present in the main memory. So here, if you look at here, the way the data or the memory was organized will be in the form of pages and all. It means, for example, if you have a main memory size of, for example, 1 gigabyte, it means that 10 power 9 bytes, right? 10 power 9 bytes approximately. So 10 power 9 bytes. And suppose if the page size equals to 4 kilobytes, so it means page size equals to 4 kilobytes means it's nothing but 2 power 12, 2 power 12 bytes, right? Whereas if the memory size equals to 1 gigabyte means its size will be in terms of 2 power exponential, it is nothing but 2 power 30, because 2 power 10 is equivalent to 30, equivalent to 1000. So therefore 1 gigabyte means 10 power 9. So it's nothing but it's like 2 power 30, right? So 2 power 30 bytes it can able to address in the main memory, right? And suppose if the memory is organized in the form of pages, as we mentioned, because in the when you are discussing about virtual memory, so the memory organization or the blocks of data that is moving between the primary to secondary memory will be in the form of pages and all. So therefore, we can view the total memory size in the form of pages. So that way, if the memory size equals to 1 gigabyte, so in terms of pages, it's nothing but 2 power 30 by 2 power 12, because each page size equals to 2 power 12 bytes. So 2 power 30 by 2 power 12. So it will be about 2 power 18. So in the number of pages in a main memory will be physically actually in the main memory will be 2 power 18 pages. 2 power 18 pages. It's nothing but 256,000 pages, right? Approximately, right? So that's the way the memory will be organized in the primary memory. And the virtual memory, the secondary memory, that the size of a secondary memory will be much higher. It's in terms of terabytes and all. So so therefore it can able to hold the multiple process, the entire process, the entire programs will be present in the secondary memory. And here I just want to introduce one more term, noted to be process and a program. So the difference between these two will be, suppose when you write a program in high level language and afterwards when you compile that, it becomes your executable file or executable program, right? Exe file. And all these things you can call it as file or a program and all. And the moment if you want to run the executable program, executable program, if you want to run the program using a CPU, it means that the executable has to be brought into the main memory, and then it has to be allocated someplace and had to be placed into the main memory. We have seen that in the previous classes and all. And afterwards, the CPU starts running the instruction by instruction sequence and all. So when you move the process, when you move the program executable into main memory, and then it will allocate some resources, whatever is required for that. And now it's known to be a process and all, because process is active entity which is to be executed by the CPU and all. Whereas the same file, if it is there in the secondary memory, it's known to be the executable file or a program, a simple program. It's inactive, it's a passive one. Like it's just like a sequence of bytes or sequence of binary numbers and all. And the moment once if you want to execute that, if you try to run the program, it will be brought into the main memory. It will be allocated some space and it allocate the CPU, and it will also allocate some other resources, whatever is required, files, whatever and all. So then we call it as a process and all. We call it as a process, right? So that is a distinction between a process and a program. A program is nothing but a passive entity. It's present in the disk memory or disk storage. And process is nothing but the same thing which you brought into the main memory. Part of that will brought into main memory for execution by the CPU. At that time, the resources will be allocated. It's active entity. It means that now it runs the program. Now it will execute the instruction by instruction and will get the appropriate output for the as per the program, as per the program and all, right? So that is the basic distinction between a process and a program and all. And now we'll see that. And here the concept of virtual memory to run the process and to run programs will brought a part of the program into main memory, then can be viewed as a process. And likewise, a several processes will be present in the main memory, and the operating system will allocate for the space for this process and allocate the resources for this process and all, right? So that way here, when the program brought into the main memory, the desired space will be allocated by the operating system, and whatever the number of pages that will be brought into the main memory, and those page locations will be place it in a page table of a particular process. Suppose a process one we brought into the main memory for its execution, then the process size may be very large. We don't bring the entire process, entire program into a main memory. A part of that or segment of that will be brought into main memory. So it may require some 50 pages. Suppose we brought only 50 pages. So that 50 pages of memory will be allocated, primary memory will be allocated. And then you have a page table for that particular process will be created by operating system. And in that page table, the page table maintains the whatever the virtual space, whatever the actual address space of the program, that is nothing but it's going to be virtual addresses that are related to the disk addresses and all. And in that, there are some pages we brought into the main memory. So the page table basically provides that actually among these virtual addresses, which of the pages are present in the primary memory, what are their locations and all. So that is the information provided by a page table, and the creation of a page table, updating a page table, all these things are the responsibilities of the operating system and all. We'll see how it will do later. So this is what we discussed basically. And if you look at here, the scenario here, address translation, this is your virtual space, nothing but a program and its entire address space. And if you brought this program into a main memory, some of the pages are brought into main memory. So you can able to see that the white portions of these segments and all, so they are available, they are placed into main memory. And the darker portions and all, they are not brought into the main memory. So therefore, they will be there in the disk access, in the disk storage and all. So for a process, for a program here, some pages will be brought in and some of them will be remains there in the disk itself. And now here, how do we perform this translation? because the CPU generates these virtual addresses and all. And from this, we need to generate the physical addresses, because the actual data that is available in the main memory, because that will be accessed by CPU and all. And so therefore, we need to translate these virtual addresses, whatever generated by CPU, to its corresponding physical addresses. And then we have to see that whether that particular physical address is present in the main memory or not. That means that particular page is present there or not. If it is there, then you can access. If it is not there, then we'll brought it from the disk and then place it, and then we'll later on we'll execute that. So how do we do that? This is the translation process, because assuming that the CPU generates a 32-bit address, for example. So in that, we know that there is a page offset. That means here the data will be organized in the form of pages. And for example, let's take a page size equals to 4 kilobytes. So in these 32 bits, the first 12 bits indicate the byte offset within the page. That means a page is a 4 kilobytes. So therefore, in these 32 bits, the most significant 20 bits corresponds to refers to the page number. Page number. And for each page, there is a space of like 4 kilobytes of data can be accommodated. That means 4K addresses will be there. 4 kilobytes of data can be there. So therefore, these 12 bits used to indicate the byte address and all. These 12 bits indicate the byte address, because the CPU will not access the entire page, because the CPU will fetch the word by word, that depending upon the bus width and all, it will fetch the word, the instruction word, which contains the as per our MIPS instructions and all, 32 bits and all. Right. So these 32 bits, to locate that where which word has to be brought out. So that will be indicated by this page offset, this page offset, this page offset. Right. And so the same way, like if you try to visualize that in the case of cache memory and all, you have a block, and the block may contain one word or 4 words or 8 words or 32 words, whatever it is. And if you want to fetch the desired word, then from the block, again, by using a word offset, we will pick up the right word, desired word, and give it to the CPU. The same way here also. So first we'll come to the page, and then once the page is available in the main memory, it means that whatever the CPU requests, that particular word is present in the is available in the physical memory. And then by using this page offset, we can able to pick up the desired word, and then we'll pass on to the CPU for its execution. And now here is that, as I mentioned, that here the address translation will be, as I mentioned, we have a virtual address, and this virtual address will be partitioned into the page offset and virtual page number. And now here to see that among these virtual pages, which of them are available in the physical memory and all. So that is provided by, that is maintained by a page table and all. That is maintained by page table. And we have seen that suppose if the page is not present, then the page fault will occur, and page fault penalty is nothing but we have seen that because you need to access the disk to fetch the page from the secondary to primary memory, and the disk consists of a mechanical components, and also therefore it takes huge amount of time. Huge amount means with respect to like a cache access or a main memory access, because they are semiconductor devices and all. So that way it takes about huge amount of time. So the penalty will be larger and all. So therefore, as far as possible, try to minimize this page fault. Try to minimize this page fault because the penalty is very high here and all. So to minimize the page fault, whatever the options we have, one thing is that while allocating the pages into the physical memory, you can able to follow the fully associative placement, so that wherever the space is there, you can able to provide. It's not like restricted way of placing the pages and all. So wherever the place is available, you can able to very flexible way you can able to allocate. It's not to be fully associative to have seen. Like the other extreme is the direct mapped one. So here we use only fully associative, so that you can reduce the miss rates as far as possible. Basically, the conflict misses and all will be overcome with this. And another one is that smart replacement algorithms, by using very efficient replacement algorithms, so that you can the miss rate can be optimized, the miss rate can be minimized and all. And the page tables, we have seen that for every program to be processed or to be executed, so the operating system will maintain a page table for every process. For every process, once the program brought into the main memory, it becomes a process. So for every process, it maintains a page table. So page table is nothing but the entries corresponds to the virtual pages which are available in the page, which are available in the main memory and all, which are available in the main memory. So therefore, each program has its own page table, and the page table entries are nothing but indexed by the virtual page number. So in principle, for example, as per the previous example, we are seeing that the 20 bits refers to the page refers to the virtual page number. So in principle, the page table should contain the entries corresponds to 2 power 20 pages. Out of that, very few pages may be present in the main memory, and the remaining pages have to be present. All the pages should be present in the disk memory and all. So the page table provides that information, and the page table is indexed by the virtual page number. The starting from the first location means the 0th virtual page, then the first, second, third, fourth, and so on. So that by using a virtual page number, you can able to directly index the page table and you can able to check it out whether this virtual page is present in the memory or not. So that you can able to check it out by using the most significant bit, known to be the valid bit and all. So with the valid bit, we'll come to know that whether this page is present in the main memory or not, right? So that way, you're using the page table and using that valid bit, you can able to check it out whether the page is present or not. And another thing is that, as I mentioned, to optimize this, the minimize the miss rate and all, we made with the memory main memory is organized, and main memory is like organized using the fully associative. It means that wherever, that means the page in a virtual memory can be placed anywhere in the main memory based on its availability and all, right? So, but as we know that in case of fully associative, the access time will be very large. That means to find out the page where it is there, it is very difficult. So that was the reason that here the concept of page table has been introduced here. A page table maintains the pages, maintains the mapping between the virtual pages to its corresponding physical pages of that particular process and all. So therefore, otherwise, actually, if the memory is organized in fully associative, then you need to search for each entry in the each page of a main memory and have to check that whether this page is present or not and all. So it is very huge time. So to avoid that, here we use the page tables so that the page tables are indexed by the virtual page number and all. So therefore, once the virtual address is available, and we'll take the virtual page number part, and from that virtual page number will be used as index. Directly we'll go to that particular entry of a page table, and then we'll check the valid bit. If the valid bit is there, it means that that particular virtual page is placed in the is available in the physical memory. And if it is not, then page fault, and then the exception will be raised, and then the operating system will fetch the page and then brought into the main memory, and again restarts. So that is the way it used to happen. So this is what you can see the page table. Yesterday we have seen that, and this is the 32-bit address. This is a virtual page number, and this virtual page number acts as index to this page table. Assuming that this page table length equals to 2 power 20 entries. Out of that, whatever the virtual page number is there, the value, and that directly gives you the index, like that is the particular entry into the page table, and that entry will check the valid bit. And if the valid bit is 1, it means that this particular virtual page is available in the memory. And here at this portion here, the remaining portion of a page table is nothing but that particular page location. That is nothing but a particular page number and all. That particular page number in the physical memory. Right? Once we have a particular page number, then we can come to know about its location, where it is available and all. And again, this page table, the starting location of, because the page table, again, it contains the entries corresponds to page numbers, right? So therefore, it also contains some information. So this page table, whatever for each process, this is also has to be present in the main memory, right? Because the virtual address will be generated, and for translation of address, you need to have page table is required. So that page table contains the information about the mapping information, right? The virtual page number to the physical page number. So therefore, this page table should also present in the main memory, so that first we'll access the page table, and then we'll check that whether the page is present or not. If the page is present, and from that you will derive the page number, and anyway, whatever the offset is there in the virtual address, the same offset will be appended to this. Now it becomes your physical address and all. That becomes your a physical address of the page, and using this physical address, we will access the main memory again, and then we'll fetch the desired word, whatever the instruction or whatever we'll brought into. So therefore, you can able to see that by using a page table, if you want to access a data from a main memory, you need to have two memory accesses are required. Two memory accesses are required. The first memory access is that accessing the page table, because the page table is also present in main memory. So therefore, to get address translation, first of all, we had to access the page table, and then from the after accessing the page table, that is nothing but it's one memory access. And then after accessing the page table, then we'll come to know that whether the page is present or not. If a page is present, then using the page table entries, we'll construct the actual physical address. And once the physical address is available, then again using this address, again we'll access the memory to fetch the desired word in the memory and all. So therefore, two memory access are required if you want to fetch the data content from a main memory and all. Right? We'll see that how do we can avoid, how do we can able to minimize this. Again, by using a caching, we can able to do that. We'll see that later, bit later. Yeah, this is a page table as I have mentioned and all. So if a page is not present in the memory, then the OS will take over, because if a page is not there means then it will be available in the secondary memory. Then we have to brought into. So therefore OS will take a control, and it will bring the a proper page, the required page, and then place it to the main memory as per the availability. And again the page table entry will be updated. So all these things will be done. And if a page is not present, it means that the page table entry contains the information about where this virtual page is available on the disk, where the virtual page is available on the disk. So that information is provided by the page table itself, because the page table basically contains, if it is there in the, if it is present in the physical memory, then the physical memory is that particular page number will be provided, and with that you can able to generate the physical address. If it is not there, then it provides information about where this virtual page is available. That means in the disk actually where it is available. In the swap space is basically that the entire virtual address or the entire program will be present in the disk and all. So by using appropriate data structures maintained by OS, you can able to fetch that. You can able to locate that particular page, virtual page on the disk, and then we'll bring it back to the main memory. We'll place it to the main memory by using appropriate steps. Yeah, this is the way you can see here. This is the page table, right? And this bit is the valid bit, and these are the whether it's a page number or the disk address where it is and all. You can see here the dark portions of this segment, the three segments, they corresponds to the pages are not present in the main memory and all. So therefore here these they provide the location where these particular virtual pages are available and all. And the other places and all, these are the locations, these pages are available in the physical memory, and these addresses and all, right? Because these are basically here the page numbers will be provided, and based on the page number and the corresponding offset, that gives you the complete physical address and all. So with that you can able to access the physical memory. Okay. Yeah, then any replacement and writes and all. So replacement means actually here a particular address space is provided to a specific process and all. And when the CPU searches for a particular particular address, particular data item, so that particular data item or that particular address is not available. Assume that it means that particular page is not available. So therefore, we have to brought that page, and then we have to place it into the memory. So if that in that case, actually here the we had to whatever the space that is allocated for a memory. There sometimes you can able to grow the memory, or sometimes if there is a restriction, if there are many processes are present, and the memory, there is no more memory for allocation. In that case, whatever the space that is allocated for this particular process, maybe assume that this particular process, the OS has been allotted 20 pages and all, and now it requires a new page. So to place this new page, out of these 20 pages, one of the page has to be replaced. So for that, again, there are policies and all, like which page has to be replaced and all. So in that case, you can make use of different algorithm, like least recently used algorithm can be used. It means that we'll analyze the page usage and all. So whichever the page has not been used for a long time, so that can be picked up, that can be used for replacement and all. And how do we do that? By using a use bit and all. There will be a reference bit will be maintained in the page table and all. And whenever the page is used and all, then the reference bit will be set to 1. It means that the particular page has been used. And again, when it's set to 1, and afterwards periodically, and again these reference bits will be reset also, will be reset. Right. So that way, every periodically, it means for in a specific 100 milliseconds around that. So each page table will be refreshed. Refreshed means the reference bits, whatever is there, they will be again set to 0 and all. So that way you can able to maintain the recent usage of the pages and all. So based on that, the specific page will be picked up and it will be replaced with the desired new page and all. So that is the use of reference bit. So we have seen that now this is another control bit that is used in the page table along with the valid bit, right? Reference bit. And there is one more bit, you are already aware of that. It's not to be dirty bit, right? If a page, suppose somebody in the when your execution, if something is written into a particular address and nothing but in a particular page, for example. So it means that that particular page is modified or the contents of page are modified compared to its original version. It's nothing but it's in the disk and all. So if the page is modified, then will that will be indicated by another bit known to be dirty bit. So with when the bit is set, it means that the page has been modified. It means that there is some write operation has been carried out on this page. So the contents have been changed. So that way you can use another bit known to be dirty bit. And basically that will be used, the dirty bit will be used. So whenever you want to replace the page, at that time we'll just check that what is the status of the page, whether it's the dirty bit is set or not. If the dirty bit is set means that page has been written by some other process, has been written. So you need to be updated in its a lower hierarchy, because the lower hierarchy also contains the page, but that page was earlier it was brought in, afterwards some modifications have been done. Those modifications have not taken care or not done in the page that is available, that is present in the disk and all. So therefore, when the page is set with a dirty bit, and when you want to replace that page, at that time, that page has to be first written onto the disk and afterwards you have to be replaced. So, and here in this case, virtual memory, the writing policy will be like write back policy and all. We don't use the write through policy because it's not practical in case of virtual memory. As we know that the access time of a virtual disk and all, it's very huge. So therefore, we generally use the write back policy and all. Okay, so and another thing is that storing the page tables, as we have seen that in principle, the page table size will be very large because the page table size depending upon the virtual address. As we have seen in the virtual address of 32 bits, so the number of pages that are that will be generated from this virtual address will be 2 power 20. So therefore, to accommodate these 2 power 20 virtual pages, the page table size also should be have the 2 power 20 entries. So again, each entry should contains the physical page number and other things, and also assuming that each page table entry will be carries 4 bytes of information, and you have these 2 power 20 pages has to be there in the page table. So therefore, imagine the size of a page table and all, like 2 power 20 multiplied by 4 bytes. It's nothing but 4 megabytes. So for every process, the page table size will be of order of 4 megabytes and all. 4 megabytes. So if you're assuming that if a main memory carries 100, main memory supports like 100 process, for example, it maintains 100 process. It means that each process has one page table and this size equals to 4 megabytes. Imagine that how much size of the can be allocated for a page tables and all. Like that itself will be like 400 megabytes. It's very huge size, right? And it's just a control information. There is nothing like actual information which is not useful for execution of programs and all. So therefore, how to store these page tables and all. So there are different techniques are there, and we don't discuss over here. Anyway, these things will come across in the operating systems. One thing is that by using a limit register is nothing but it just whatever the number of pages that are allocated in the physical space in the physical memory, and only those pages only will be shown in the page table and all. It means suppose you brought only 200 pages into the page table for in the main memory, and your page table will be maintains only those 200 pages, and so the page table size also will be limited to 200 pages and all. It means that the page table just carries the entries corresponds to its physical pages only. It won't carry the entire the virtual space and all. Suppose if a CPU generates some virtual address and if it is not present, then we'll brought that page into the memory and then the page table size will be increased to one more entry. So that way, using a limit register, we can able to maintain the page table size, whichever is just required to maintain the physical pages, whatever to map the virtual pages to physical pages, that much size will be there instead of providing the entire page table and all, right? So that is by using limit register. And as we know that when you are allocating memory for a program and all, so we have seen that there are two entities that will be growing. Like one is the stack and other one is the heap and all, like dynamic data, where the size of a memory will be increased as the program starts running and all. Right. Similarly, stack also. So therefore, to accommodate those things, a process will be maintained by two page tables, which is one will take care of the stack and other will take care of the heap plus the other instruction memory and all. So this is here also we use the limit registers corresponds to these two tables, and it's just similar to this only. And another one is hash page table. It's nothing but we use the page table instead of maintaining a page table of 2 power 20 entries. So here we'll maintain the page table as I mentioned, like with whatever the number of pages that is accommodated in the physical memory. Only that much size only will maintain. And for that we're using a hashing principle. That means whatever the virtual address is generated, first we'll hash that, and that hash function will provide you the corresponding physical page and all. So that way the page table size will be can be limited to whatever the number of entries that supported by the physical memory, only that many entries used to be there. And there is another one, multi-level page tables. Yeah, this is nothing but we'll maintain instead of a single page table of 2 for 20 entries. We'll split that page table entries into again local page tables. I'll say that page tables at secondary level and all. And these page tables of secondary level are maintained by another page table. So it's something like that. For example, your page table size equals to 2 power 20 entries. Instead of maintaining one page table of 2 power 20 entries, so what we do is that actually we will maintain some thousand sub page tables. Each page table contains again a thousand entries and all, right? Because we need to maintain 2 power 20 entries. It's nothing but 1 million entries. So instead of having one page table, we'll keep that 1 million entries in the form of 1,000 page tables, where each page table supports 1,000 entries, 1,000 entries. And again, all these 1,000 page tables starting addresses, their locations will be maintained by another page table at a primary level. So that way we'll maintain the two-level page tables, so that it's not that all the tables are required or to be placed into the main memory. Most of the tables will be there in the virtual memory or in the disk storage. So whichever the page tables that are required, so that will be brought into main memory. So with that, the page tables can be it's no need to require the massive page tables to be placed into the main memory, right? The same way like a page tables also, similar concept and all. Anyway, these things we'll discuss more details in the operating systems when you're discussing about. Yeah, the next thing is that, yeah, as we have seen earlier, I already mentioned, in the case of virtual memory, to access a physical memory, you need to have two memory access times are required. The first memory access is that for address translation, that means to get a physical address, and the second access will be after knowing the physical address to get the actual data. You require one more access is required. So to minimize that, to speed up or to increase the performance and all, we can use a buffer known to be translation lookup buffer. It means that whatever the recent translations that we made, that means when the CPU generates its virtual address, we convert that virtual address to the physical address, and then by using physical address, the memory is accessed. So this recently converted the virtual address to the physical address maps, whatever is there. So those will be maintained by a cache. Those will be maintained by a cache that is present in a CPU and all. So whenever the CPU generates a virtual address, first it will check with the cache, because the cache maintains the recently used the virtual to physical address mapping and all, right? So that it maintains that. First it will check the cache. If the cache contains that particular virtual address to the physical address mapping, if that particular translation is available in that cache, then it directly make use of the cache, and then it can generate. Then it generates the physical address, right? Otherwise, to generate that physical address itself, you need to have one memory access. It means about 100 nanoseconds is required. But now instead of doing that, we'll place that the mapping itself directly into the cache, and then accessing cache will take about 1 nanoseconds or 2 nanoseconds, right? So therefore, just the normal one cycle itself, we can able to get the physical address, and then we can access the physical address in the next axis. right? So that way you can able to minimize or can able to optimize the time for accessing the memory instead of using a page tables directly by using a cache where the cache maintains the recent the mappings or recent references that are used between the virtual memory to physical memory, and based on that you can able to access the physical memory, right? So that is the concept of here the fast translation using the known to be here the translation look ahead buffer. TLB means translation look ahead buffer. We'll see that how it used to be and all. Like so with that we can limit the instead of two axis only one axis is sufficient here in this case, and the specifications of this translation lookahead buffer will be something like this. So if you look at here the translation lookahead buffer, it will maintain the entries like in the range of 16 to 512 entries it will be maintained, right? 16 to 512 entries it will be maintained. And for fetching, suppose if the particular virtual address mapping is available in the main in the cache and all, it takes about, as I mentioned, one cycle, zero point 0.5 to one cycle if it is a hit. Suppose if it is a non-hit, then again, if it is a miss means, then again you have to go to the page table, then another 100 nanoseconds, 100 cycles may be required in the case. And the miss rates will be very small, like 0.01% to 1%. And the misses can be handled here will be either hardware or software and all. You can able to do that. And this is the scenario by using translation lookahead buffer. So this is a buffer. This is the cache here, the TLB, where the TLB maintains a tag. The tag is nothing but your virtual page number, right? The tag is nothing but your virtual page number from the virtual address. And here this is nothing but your physical page number. This is nothing but your, because here by using a page table, using a virtual page, you directly go to the corresponding index, corresponding location in the page table, and then you can able to see a physical page number. And from that, you can come to know what is the physical address. Now this TLB maintains this virtual page number, a tuple of virtual page number, a paired address of virtual page number, and its corresponding physical page number. So both will be maintained by the cache and all. So whenever the virtual address is generated, first the consult the cache, it just check the tag entries and all, like whether the virtual page number like matches with any of these tags and all. If it matches with any of the tag means it means that a corresponding physical address is available here, right, directly. And then you can use that, because accessing this cache is taking only one cycle. Whereas if you want to access the page table, it takes about 100 cycles and all. That's the difference. So therefore, in one axis itself, you'll get a physical address, and then using the physical address, you can able to access the physical memory, and then the corresponding data will be accessed by CPU. And one more thing, as we have aware that the CPU first check the cache, not the physical memory and all, right? The CPU first check the cache, right? The cache means this is another cache where it just maintains the relation between the virtual addresses to the physical addresses and all. Once the physical address is available, right? Once the physical address is available, then we'll check the cache if that particular data word is present in the physical memory, the cache or not. If it is present, then you can able to get much faster compared to accessing the physical memory and all. So therefore, you can see that the scenario will be something. Actually, it will be like this. So this is your TLB, right? And suppose the cache hits, suppose if the TLB contains the physical address for the given virtual address, then from this physical address itself, it can able to directly consult the cache. Suppose if this physical address is present in the cache, it means that a particular block is present. Then from that, you can able to extract the desired word and all, desired word, right? So if it is not present, then it will go for the main memory to bring this particular block, and then it can be accessed the way we have seen earlier and all. So now we'll see here, like for example, when you check the virtual address for in the TLB, there may be sometimes the TLB miss may happen because the TLB maintains very few entries, like 512 maximum, 512 entries as per the specifications seen. Whereas the page table size will be much larger. It will be like order of like thousands and much more than that, like a 2 power 20. And whereas it contains only 2 power 512 means 2 power 9, 2 power 9. See the difference between the cache versus the recent references versus the actual page table, right? So now if suppose if the TLB misses, Means TLB sometimes the entry may not be there in whatever the virtual page you decide, that may not be recently accessed, so therefore it may not be present in TLB. So that may happen, right? So therefore, if the page in this case, there are two things. One thing is that the page is maybe there in the memory, or it may not be present in the memory also. If the page is in the memory, then what can be done? You need to, if the TLB miss occurs, then immediately check the page table if the page is available in the memory or not. If it is in the memory, then by using appropriate hardware, you can able to bring that contents to the cache, and you can able to update the TLB also, and then you can rerun. Suppose if the page is not present in the memory, for example, then in that case, page fault will occur and the appropriate things will happen. That means the page will be brought from a secondary memory to physical memory first, and then again from there to cache, it will update. So that way it can be done. Right? So the TLB misses means there is a possibility of the page may be present in the page table or in the memory, physical memory, but it's not there in the, it's not updated in the TLB because it might have been brought in, but so far it may not be used. So in that case, the TLB miss may generate. So if the TLB miss generates means the next level will be like your page table, right? Page table will much larger volume and much larger in size. So therefore, the pages maybe the physical pages may present there. So therefore, it can able to check it out. Yeah. So this is one way, and this one, as I mentioned, the TLB miss occurs. It can able to handle by using appropriate hardware and software, and the hardware is much faster. But what happens is that actually, if the page table is complicated, if it's very large in size and all, then handling with the hardware requires a complex structures and all. That means more additional hardware is required. So in that case, you can use the software with the efficient way, so that you can able to manage. That means you can able to find that particular page, and you can able to update the entry and all. So the software means what happens? Suppose the miss is there, handling by software is nothing but it generates an exception because the table, the mapping is not present in the cache. So it means that it's not there. Then you have to check that whether it's there in the page table or not. So it means that whatever the current instruction that has to be stalled. So therefore, it generates an exception, right? An event occurred where the particular entry is not there. We have to check that we have to check. We have to get that entry. We have to get that particular data or whatever. So for that, we need to check the page table and the physical memory. And if it is not there, page fault. So those things. So therefore, first it generates an exception, and with that exception, it can able to handle the misses and all. That's what the page table handler and all similar to that. And the page fault handler is nothing but suppose if the miss occurs at page table at the this one at the TLB. TLB means translation lookout buffer. If it is there, if it is a miss there, then it may be present in the page table or in the physical memory. Suppose if it is not there in the page table means it's a page fault. If it is not there in the page table means that particular page, that particular address which contains the page, that page is not available in the physical memory. It means a page fault has been occurred. So page fault has occurred means that you have to fetch from the disk. It means that from the page table you will come to know that where that page is available in the disk and all. Then you have to bring that page. So while bringing that page, you have to see that if the page has to be replaced or not. If a page to be replaced means then you have to see that which page has to be replaced. And in that page, if there is a dirty bit is there, then we have to take care. We have to write into that and you have to be replaced. So these things has to be taken care using a page fault handler and all. And this is what I already mentioned, like how the TLB and cache will be interact. Because from the TLB, you can able to, it's again a small cache and all, where it just maintains the mapping, like virtual address to physical address and all. And if the TLB hit is there, means you can able to get a physical address in the one cycle itself, right? And then after you get a physical address, you need not go to the main memory, because for accessing main memory it takes about 100 nanoseconds or 100 cycles. Instead, actually, you can able to check the cache, the another cache, either instruction cache or data cache. It will check the cache and all, right? It will check the cache. So for checking the cache and all, this way you can use, because you will get a physical page number and offset will be there from the virtual address. So you will get a physical address will be generated, and this physical address will be partitioned as per the cache organization, as per the cache organization. Here, if you look at here, the cache is organized in the form of blocks, and where each cache contain here is indexed by the 8 bits and all. It means that number of cache entries equals to 256, right? And the block offset equals to 4. It means that there are 16 blocks can accommodate in that. That it's nothing but it's like a set associative cache. It was organized as a set associative cache, and the number of sets equals to 2 power 8. It like, and each set contains like 2 power 4 blocks, 2 power 4 blocks and all. So that way you can see based on this organization, you can able to based on this splitting the number of bits and all. So this 18 bits corresponds to tag, and then you can able to check it out whether the physical address is present in the tag by using this circuit valid bit and other things. And if it is present, then you can able to fetch the desired block, or because there are 16 blocks are possible in this set and all. Then by using this block offset, you can able to fetch the desired block or the desired word, right? So that way you can able to do it. And again, for getting these the contents of a cache and all, there are two ways. One is that using this one, you first check the TLB, and from the TLB you fetch the physical page number and then physical offset, the page offset, and form the physical address. That means the entire translation has to be done. It takes about reasonable amount of time, and then afterwards the cache has to be checked by using this physical tag, physical address tag and all. So again, to minimize the time, there are sometimes the caches will be organized, indexed based on the virtual page number directly. Virtual page number directly. So in that case, the formation of physical address is not required here and all. Means that first of all, based on the virtual address, we first will check that whether this virtual address is present in this TLB or not. If it is present, then based on this virtual page number directly, you can able to index the cache. You can able to search the cache and all. You can able to search the cache directly. Like that means we are bypassing this TLB access here because just we are comparing with the tag, and if it is found, then immediately using this virtual page number, the cache will be searched. So that is known to be virtually indexed cache and all. And there are certain problems with that again by using the virtual indexed cache and all. There may be happens that there are multiple virtual addresses may refers to the same physical page. There are some aliasing problems are there that can be again resolved by using some other ways. Anyway, we are not going to that details, but for improving the efficiency, one way is that actually instead of going with the physical tag, you can also use the virtual tag. Virtual tag means whatever the virtual page number is there, directly use this virtual page number to access the tag, to access the cache, So with that, a cache entries can be accessed directly using virtual page number itself. And so these are the different possibilities, like because you see here we are using a TLB, right? And if the TLB hit, then the physical address will be generated. And with the physical address, you can able to access the cache. Suppose if the TLB is missed here, the TLB hit is not taken place. That means the virtual page is mapping is not there in the TLB. It means here you have a TLB miss. At that time, you had to consult the page table. We had to check that one whether this virtual page number is present in the page table or not. It means that whether this virtual page number is present in the main memory or not, right? So for that, we had to consult the page table. So with that, we will come to know that. So even though here the virtual page number is not present, but it is there in the physical memory and all. So that way we can able to do that. So therefore, if you check these various combinations like a TLB, cache, and page table, there are three here. That means here that sometimes when you try to access the TLB, you may get either hit or miss over here. And afterwards, suppose the TLB hit is there, and maybe at that for that particular physical address, the block may not be present in the cache or may present in the cache. It means that after the TLB hit or miss, again the desired content, desired block may present or may not present in the cache. It means again here a hit or miss may occur, right? And again, if the TLB miss is there, and at that time we need to consult the page table. It means that the TLB, that means the TLB, the virtual page number is not present. So then there may be a chance that the page number may present or the virtual page may be available in the physical memory through the page table and all. It may hit here. If it is miss here means then we have to bring the page fault will be there. So therefore there are three possible ways, like each will take either hit or miss may be there. And here what is the various combinations, what is the corresponding possibilities over here. So those were mentioned over here. These are very there is like very intuitive ones. and also it means that here the TLB hit, the page table hit. TLB hit means automatically a page table hit will be there because the TLB maintains a virtual page mapping means that will be by default, it will be there in the page table and all. It's nothing. There is nowhere that actually TLB hit and page table miss will not happen at all. That's the reason you can see here the bottom three entries and all. You can see that the TLB hit, and if you try to see that the page table miss means it's impossible. It cannot happen at all. And similarly, TLB miss and page table miss and a cache hit also not possible because what it means a cache contains the physical page or the desired virtual page, but that virtual page is not present in the TLB and page table because the page table actually contains that whatever the virtual page is present in the physical memory, so it is maintained by page table. So if you miss in the page table and finding a hit in the cache is impossible. It's impossible, right? So that way, these three, you can see that the bottom three are the impossible cases and all. And yeah, this was the final thing. Just there's nothing to explain over here. And this is just a sequence of process. Like once the CPU generates a virtual address, first it will check the TLB cache, TLB, like the translation locate buffer, because the TLB maintains the recent mappings, right? So therefore, the first check the TLB. And the TLB, it may find the TLB or it may not find in the TLB. If it finds the TLB, it means a TLB hit. That means whether it's a TLB hit or not. If it is a TLB hit, then take this path. If it is TLB miss means, it means that it's not present in the TLB. So therefore, by using either hardware or software, you can check it out in the page table. It may be present in the page table or not. If it is present in the page table, then again it will be TLB will be updated, and again then again we restart, then we'll get the TLB hit, right? If it is a TLB miss means then that particular mapping is not there in the TLB. Then we'll go on, that means if it is a software way you can handle me, then the exception will be generated. Then we'll check the page table and all. If it is present in the page table, then the TLB will be updated. If it is not present in the page table, it means that page fault, then the page fault mechanism will take care, and then the corresponding page table, and again these things will be updated. Suppose, for example, if this particular mapping is present in the TLB hit, it means that using the TLB hit, you can generate the physical address directly in one cycle itself. And once you get a physical address, then we need to check whether we have to write or we have to read from that particular location. So if you want to write that, because the reason is that sometimes some pages are write protected. That means that the data or instructions, whatever is there in that particular pages, they cannot be written. You can able to read that, but you cannot write into that pages and all. So therefore, once the TLB hit is there, then you have to check that whether you want to write or whether you want to read. So therefore, if you want to write, for example, if you want to write, then you need to check that whether the page has the write access bit is set or not. As I mentioned, some pages they are write protected. So in that case, the write access bit will be 0. And some pages will be, they can read and write access will be there. In that case, the write access bit will be 1. So if you want to write into the page, that means with the CPU want to write something into the particular page, particular location in a page, then you will check that whether the write access bit of the particular page is set or not. So if it is set means that you can able to write into that. So if it is a set, that means if it is yes, then you will write, that means try to write into the cache at that particular location, right? So if you try to write into the cache, you need to check that whether that address is, whether that particular block or word is present in the cache or not. Whether that particular word or block present in the cache, because you got the address and all, and with that you are checking whether you want to write or not. If you want to write, then you go to the particular cache location, you have to check whether the particular location or particular block is available or not. If it is available, then you can able to write into that. Then in that particular block at the particular word, whatever you want to write, you can write into that, and you can set the dirty bit of that particular block, and then accordingly you can do that. And then you write into the write buffer also for later doing that. Suppose the cache hit is missed. If that particular location or particular block is not present in the cache, for example, then what happens? The cache miss occur. If cache miss occurs, then what happens? Then you stall the pipeline, and then you fetch that particular block from main memory and again try to write into that, right? And here, suppose if the write access bit is not there, write access bit is not set, it means that the write protection, the particular page is protected from the write. right? That means like you cannot write simply into that particular page. So in that case, the write access bit is not set. So therefore, no. So therefore, write protection exception will be raised. That means if you want to write something into the page where that page will be protected from writing, so in that case, the exception will be generated and you'll get a message. You cannot write into the page kind of a thing. And similarly here, we are checking that whether you are writing or reading. If you are not writing, it means that you are reading from the data. You are reading from the cache. Then again, you have to check that whether the particular cache entry is there or not, whether the particular page is, whether the particular physical address block is there or not. If it is a hit, then CPU can access that and can move forward, can execute the data, can execute the instruction and all. And if it is not present, then again the cache miss occurs, and again you have to fetch the block and then you have to read. So therefore, these are the various possible actions that can take place from a virtual address to the execution of an instruction and all. There are various possibilities can occur, whether it's present in the TLB or not, and afterwards whether you have to write into that or read into that. If you want to write into that, you have to check that whether the write access is there or not, and then afterwards whether the particular entry is there or not in the cache. So all these various possibilities you can able to check it out. And finally, the last part is the memory protection is nothing but actually here, when you look at here in the memory, in the main memory, it's not that one process will be there. We are keeping a multiple process into the main memory, or the multiple users will be supported by you have primary memory to perform their various tasks and all. So in that case, actually here we need to see that a process should not access some other address space, some other process address space. It means the process cannot write something, or process cannot read something from the other process addressing area and all. So it means that each process has to be protected from writing something or reading by the other process and all. Only that particular process is allowed, or an operating system can able to access that particular address space and all. So therefore, that way, when you perform this multi-programming and other things, when you are allocating a space and all, so here the memory protection means because the memory supports the multiple process and all. So therefore, each process has to be protected from other process to write or read their own contents and all, right? So it requires the OS assistance and all. And for doing that, actually here the OS will make use of various things. OS will make use of the different two modes of operation, not to be supervisory mode and user mode, right? And also it uses some specific instructions, not to be privileged instructions, and these instructions will be operated by only OS during the OS mode, or not to be kernel mode, supervisory mode. Like for example, you want to perform certain disk transfer and all. Like user program cannot do that. User program don't have a right to perform a data disk transfer or a keyboard data transfer and all. So all the things will be performed by the OS. Otherwise, no, suppose if you allow the user to do that, means user may misuse that, and he will he can access the other process addresses. He can able to may perform the unwanted things also. So that's the reason that the OS protects the all the process, including itself also. Like OS is also a software, no, it's a piece of code. So nobody allowed to write into the OS kernel or OS address space. At the same time, each process is allowed to write or read only from its address space only. It cannot allow to access the address space of other process or the OS process. And for that, the OS will do all these things, will perform these things by using different modes of operation. One is the user mode and supervisory mode, right? And similarly, there are some special instructions will be there. With that instructions, only the OS can handle those instructions, right? The users cannot access those instructions and all. And again, these instructions will be accessed only by the in the privileged mode or in the supervisory mode. So by using these various like provisions of the OS and all, it can able to protect the various processes that are lying in the memory and all. So that way the will this that way the OS can protect the other process which are running concurrently by the CPU and concurrently making use of various resources and all. Right. So yeah, that's all I want to cover in this particular memory hierarchy. So we'll stop here, right? And let's take a break for 5 minutes. and then afterwards we'll just start the introduction to the operating system and overview of operating system and so on. So we'll stop here. Okay, and so those who have any questions, we'll discuss over here. Uh, so let me stop the recording so that the other part can be again afresh. We can record.